thermochemistry here. Now in this we are going to learn very simple two laws here, right? So let us go for it. First one is Lavoisier and Laplace law. So this law is very simple. What it says, suppose I am writing an equation here, H2 plus half of O2 gas giving you H2OL, and I'll be writing here delta H is equal to minus 68 kilocalorie per mole, suppose, right? This is a thermochemical equation which I have written, okay? Now suppose if I reverse the reaction here. So reversing the reaction, it will seem like as if H2O liquid is getting converted into H2 gas plus half of O2 gas. So in that case, delta H will become plus 68 kilocalorie per mole, right? So that means according to this law, what you should take care of, that if at all I am reversing any reaction, then the magnitude of this particular delta H, it is not changing. Magnitude of delta H reaction does not change. Only thing what is changing is the sign of basically this delta H is getting changed. So sign reversed, I'll write down. Sign reversed. Got it? That's only your Lavoisier and Laplace law. Write it down. I'm not giving you a statement. It is very clear. If you are reversing the reaction, simply you reverse the sign. Okay? So if a reaction reversed, then magnitude of delta H remains same. Only sign of delta H reverses. That's what is Lavoisier and Laplace law. Is there any doubt in this? It is a very simple law. Simply reverse the reaction, reverse the sign of delta H. Okay. Can we proceed further in case if you have written it down? Okay, now let us go for the next one, which is Hess law of constant heat summation. Hess law of constant heat summation. Or simply we call it as Hess law. So what does it state? Suppose I am carrying out a reaction here, A to B, right? That means reactant is A, we are ending up at product B. Now there will be definitely some amount of heat liberated or absorbed in this reaction. So let us call that as delta H reaction. So Hess law simply states that whether you carry out a reaction in one step or more than one step, so the total amount of heat which is absorbed or liberated in a chemical reaction, it remains same. Reason being here, do you know that enthalpy is a state function? So it only depends on state. You are starting from A, that is basically A as a reactant, and you are ending up at B, which is your product. So whether you carry out that reaction in one step or more than one step, delta H for that reaction is going to remain same. Okay. So here I'll be writing this as A to C, C to D, D to B. So I can write down delta H1, delta H2 and delta H3. So simply delta H of the reaction is equal to delta H1 plus delta H2 plus delta H3. Is there any doubt to anyone here? It is a very simple law. So I'll write down the total amount of heat absorbed or liberated in a chemical reaction, remains same whether reaction is carried out is carried out in one step or more than one step, or more than one step. I hope this point is clear to you. Please write it down, then we'll see a simple question based on this. So we are not going to call this as so much a bigger name here, simply Hess law. Constant heat summation is meaning the same thing. That means if at all you carry out a reaction in one step or more than one step, the heat absorbed or else released here in a chemical reaction is not going to change, because you are starting at A, you are ending up at B only. Quickly write this down. Then I'll give you a small question here, very basic question, so that you have the understanding of Hess law. As such, Hess law will keep on coming, right? That means when we are learning enthalpy of formation, when we are learning enthalpy of combustion, it will keep on coming there. Can I proceed to the next one if you people have written? Done. Chalo, write down one question then. Given carbon solid plus half of O2 gas giving you CO gas, delta H1 is minus X kilojoule per mole. Then CO2 gas getting decomposed into CO gas plus half of O2 gas, delta H2 is plus Y kilojoule per mole. Find delta H for the given reaction. I'm writing down that reaction. For that reaction you have to write down carbon solid plus O2 gas giving you CO2 gas. For this reaction you have to find out delta H. Find it out and let me know. Correct, Remant, good. It's a very basic question which I have given you so that you get the idea of it, Hess law. So in this question, you should think that this is your target reaction, because for this reaction you have to find out the delta H. And you should be always worried about, kind of reactant and product, and except oxygen, because oxygen automatically gets balanced there, right? So the thing is, in the target reaction, you want carbon in the solid form, and let us say this is reaction number 1 and this is your reaction number 2, right? So we want carbon solid, that to 1 mole. So we are getting from the first equation. So I'll write down reaction 1. Then you want basically CO2 here as a product, but in the given reaction it is present in the form of reactant. So you reverse it. Reversing means you're going to write down here minus reaction 2. So basically I'm going to write down simple thing here, delta H of the reaction, that is equal to delta H1 minus delta H2. Now delta H1 is how much? Minus X, and this is minus Y. This will be your answer, minus X minus Y. See, here in thermochemistry, things are very simple. Only problem is you people do not pay attention to plus or minus sign, and we are in little bit of hurry of calculating. Please do not be in little bit of hurry. Give extra few seconds, we will end up with the correct answer, right? Now let us go further here for learning standard state. Standard state. Yes, Chaitanya, I think, Chaitanya, check your answer. Tejaswini, you are correct here. Ganesh also correct. Sai Mahita also correct. Okay. Now when it comes to basically standard state, according to thermodynamics, what is the standard state of a substance? If you take any substance, what do you understand by the standard state? Is the temperature fixed there? Is the temperature fixed there when I am talking about standard state? Is the temperature fixed? Is there any temperature which I am calling as standard temperature? Yes, what is that? No, there is nothing like standard temperature there. No. if at all I take any substance, so according to thermodynamics, the standard state of that substance would be what is the most stable and purest form of that substance which could exist at 1 bar pressure. And temperature could be anything. Temperature could be anything. Standard temperature does not mean 25 degrees Celsius. Are we getting it? So what is the form in which a particular substance is existing in its purest form, most stable form at 1 bar pressure? Temperature could be anything there, right? That is your standard state of the substance, right? And if at all nothing is given, we take it as 25 degrees Celsius, but 25 degrees Celsius is not a standard temperature. So be aware of it. So here I am writing thermodynamic standard state of a substance is its most stable pure form present at 1 bar pressure and any temperature. And if temperature is not given, then take it as 25 degrees Celsius, right? So if at all I am talking about that I am having a block of iron, right? Let us say that block of iron is present at 500 Kelvin and that is pure iron solid I am having, right? And that pure iron solid is present at 1 bar pressure and temperature, let it be 500 Kelvin. Then also it is standard state of iron, right? Temperature could be anything, 500 Kelvin, 200 Kelvin, anything. But the thing is, you are having 1 bar pressure, what is the purest, most stable form of that substance, that is the standard state of it. So here I will be writing this for solids or liquids. Standard state means their pure form at 1 bar pressure. And for gas, standard state means pressure of the gas should be 1 bar. And if at all I am having for any substance present in solution, so for that substance concentration should be 1 molar. I think you will be able to relate here that basically all of you know about standard hydrogen electrode. All of you know about standard hydrogen electrode. You have already read in electrochemistry, right? Now in that, do you remember we are calling it a standard hydrogen electrode because the pressure of the hydrogen gas was 1 bar and the concentration of H plus ion which we are taking is 1 molar, right? So are you able to relate now? So any solute which is present in the solution, I'll say that its standard solution, if at all its concentration is 1 molar, for the gas pressure should be 1 bar. I hope it is clear to all of you. Yes? Are you able to relate that? Good. Now we are going to make a table here for element and their standard or reference state. Standard or reference state. And this table you must remember, and as such there is no logic behind this table. It is a random assumption which scientists have taken and you have to follow that. You have to remember it. Getting it? So we are going to write down for carbon in the graphite form, for sulfur in the rhombic form, for phosphorus in the white form, for hydrogen H2 in the gaseous form, for oxygen O2 in the gaseous form, for nitrogen N2 in the gaseous form. Similarly, fluorine, chlorine, they will be existing as F2 gas, Cl2 gas. For bromine, Br2 liquid. For iodine, it is I2 solid. For all metals, I am writing M here. For all metals except mercury, I'll be writing M solid, that is their standard state. For mercury, it is Hg liquid. Because this particular table what we are writing, sometimes scientists give upon, they have chosen it based upon sometimes abundance, sometimes based upon the stability. So there is no logic, because if at all you have little bit information about phosphorus allotropes, so we know that it is red, black and white, and black will be the most stable form of it. Getting it? But the thing is, according to thermodynamics, they have taken white as, kind of most stable. So the thing is, do not try to find any logic here, because there is no logic, sheer assumption by the scientist, which we have to remember. Is this point clear? Finish writing it, then we'll proceed further. Done now? Okay. Now let us go further for learning various types of delta HR. That means various types of enthalpy of reaction. R means enthalpy of reaction. First one is, and this is very important as far as thermochemistry is concerned, because unless and until you are having an understanding of understanding of the terminologies there, till that time you will not be able to solve the thermochemistry problem, right? So here we are going to see first one, which is standard enthalpy of formation. So when we say standard enthalpy of formation, that means delta HF naught, or else we can write down delta FH naught. Either way it is fine. It is standard enthalpy of formation. So I'll be writing down the definition here, right? And then I'll explain you after that. So all of you can write along with me here. So I can write down here the change in standard enthalpy when 1 mole of a substance is formed from its constituent elements present in their standard or reference state. Now what is the meaning here? Suppose I want to form, or else I want to write down enthalpy of formation of some product here. Let us say I want to find, or else write down the standard enthalpy of formation of CH3OH, right? Now one thing you must be very clear, that you are going to form 1 mole of the substance. That is fixed, okay? Now what are the constituent elements of CH3OH? Do you have carbon, hydrogen and oxygen, right? So the thing is, you have to make 1 mole of this compound from its constituent elements, which are carbon, hydrogen and oxygen, and they should be existing in their reference state. That means, what is the reference state of carbon? Reference state of carbon is carbon graphite, and reference state of hydrogen is H2 gas, and reference state of oxygen is O2 gas. So look here how I'm writing the equation. So I'm going to write down, this is from carbon graphite, then you are having basically H2 gas, and then you are having here O2 gas, right? So you are going to make all of them, like from their constituent elements in the standard state, you are going to make 1 mole of it. Now balance it. Here hydrogen how many? 4. So I should be writing 2 here. Oxygen how many here? 1. I should be writing half. Do not try to multiply 2 over here, because the moment you write down 2, it is not enthalpy of formation. Getting it? So I'll be writing here delta H naught for the reaction, that is equal to delta H naught formation for CH3OH liquid. So you should understand one thing. You should always read it like that. This is the reaction for which you are finding out delta H when everything is present at their standard state. That's the meaning of naught. Okay. And what is this reaction representing? Is it representing the formation of CH3OH? That's what we are writing here. Delta HF naught CH3OH. Are we able to understand here? Getting it? Now I'll be writing few more compounds. You have to write down the reaction here. I'll give you a little bit of time. Try to write it down. NH3 gas. For these two you write down. Delta H naught for the reaction, that is equal to delta HF naught for CaCO3 solid. Delta H naught for the reaction, that is equal to delta HF naught for ammonia gas. Write down the equation here, everyone. Fine, if you have written, need not write down it. Somebody is writing CaCO3 not possible. Why not possible? You can write down for anyone now. See, the person who has written that, you are reading the NCERT but incorrect line of that. Go to the next paragraph. You will get the correct answer. For CaCO3, I have asked you to write down the enthalpy of formation of it. So what are the elements here? Calcium, carbon and oxygen. So write down here for calcium, calcium solid plus carbon in the graphite form. Plus you are going to write down O2 gas and this has to be 3/2 O2. Right? It is balanced. No, Sai Mahita, you are wrong, beta. That is not the formation reaction at all. Formation reaction means you should be forming 1 mole of it from its constituent element in their standard state. That's what I'm trying to explain, right? Here you are having 1 mole of it. Constituent elements are nitrogen and hydrogen. So for nitrogen, it is N2 gas and hydrogen H2 gas. That's its like standard state. Half of you will be writing this will be 3/2. Do not try to multiply it by 2. I hope it is clear. Yes, Gautami has written it absolutely fine. I think Reshma also, Preeti also, Anil also. Good. Now, let us go for the next thing here. I hope it is clear to everyone. Okay. Now, if at all, sometimes it may happen, they may give you a reaction and they may ask you to find out delta H naught for the reaction. Okay. Now, the thing is, they may provide you enthalpy of formation data for the product and reactant. So at that time, you can easily do summation of standard enthalpy of formation of the product minus standard enthalpy of formation of the reactant and find out enthalpy change in that reaction. So I'm going to write down here formula delta H naught for the reaction, that is equal to summation of standard enthalpy of formation of the product minus standard enthalpy of formation of the reactant. So P is standing for product and R is standing for reactant. Even you can apply at the non-standard condition also, there is no harm in that. That means simply I'll be writing delta H for the reaction, that is equal to summation of enthalpy of formation of the product minus summation of enthalpy of formation of reactant. Right? So this you have to apply if enthalpy of the formation or else standard enthalpy of formation of reactant and product is given in the question. Right? Now I'm going to write down a note which is again going to be important here. Standard enthalpy of formation of all the elements in their standard state is 0. Meaning, suppose I am writing here standard enthalpy of formation of O2 gas. So here it will be 0. Reason being, for the formation of O2 gas, what is the element which you are going to take? Oxygen only, na? Element in its reference state is oxygen, reactant is also same, product is also same, so delta H will be 0. So all those elements which we have listed in that table, right, whose reference state we have written, so standard enthalpy of formation of all of them is going to be 0, right? So I'm going to write down here, I'm not going to write down the entire list, just few of them. Delta HF naught for carbon in the graphite form, that will be 0. Similarly, delta HF naught for bromine in the liquid form is 0. And I'm writing etc. means that entire list will be there here. Got it? First finish writing this, then we'll proceed for a question here. Okay, so let us write down one question here. Find delta H naught of the reaction. Reaction I am writing here, aluminium solid plus Cr2O3 solid, giving you Al2O3 solid plus chromium solid here, given delta HF naught of Al2O3 solid is minus 400 kilocalorie per mole, and delta HF naught of Cr2O3 solid is basically minus 200 kilocalorie per mole. Find out the answer and let me know. I've given you a very basic fundamental question here. Yes, I think Raymond has given correct answer, Hanudeep also, Reshma also. So the thing is, simply you have to write down delta H of this reaction. That will be summation of enthalpy of formation of product minus, in fact delta H naught I am writing here, delta HF naught of the reactant here. In this case, simply I will be writing delta HF naught of Al2O3 minus delta HF naught of Cr2O3. Because for aluminium solid and chromium solid, it will be 0. Just now we have written now. So I'll write down since delta HF naught for aluminium in the solid form, or else delta HF naught for chromium in the solid form, that is going to be 0. So simply minus 400 minus of minus 200, we'll be getting minus 200 kilocalorie per mole. Able to get it? Then I'll give you next question. I hope everybody has done it. Good. Now next question. Find delta HF naught of HBr in the gaseous form. I'm writing H2 gaseous plus Br2 liquid, giving you twice of HBr in the gaseous form plus 80 kilocalorie. Yes, very good. Those who have solved it, wonderful. Go for the next one. Yes, Raymond, correct. Good. See, first of all, you should be able to see that this is exothermic reaction. So I should be writing H2 gas plus Br2 liquid, and that is written as twice of HBr in the gaseous form, and delta H is minus 80 kilocalorie per mole, right? Now this reaction is not basically the enthalpy of formation reaction. I can say that delta H naught of this reaction is actually twice of delta HF naught of basically your HBr in the gaseous form. So basically you are having minus 80 upon 2. You can easily get your answer as minus 40. There is one more way which you could have gone for. That is, I am writing this equation H2 gas plus Br2 liquid. I am writing this as twice of HBr gas. Delta H here is minus 80 kilocalorie per mole. Now for the formation you require basically 1 mole this side, so simply multiply by half. Whatever operation you are doing here, this side also the same thing, you will be getting minus 40 then. That's your answer. So anyway you can go for, you should understand, and purposely I have written like this because the thing is sometimes they may ask you which of the following relation is correct. So you should be able to identify. This is the case now, H2 gas plus Br2 liquid. For the formation, half of this, you are writing HBr in the gaseous form. So this is your enthalpy of formation reaction of HBr gas. So if you multiply by 2, then only you will get it. So from there only we are saying this thing. Got it? Any method is fine, beta. Any method is fine till the time you are arriving at the correct answer. For solving a particular problem, there is no particular, there could be more than one way. Whichever way, if it is fundamentally correct, there is no issue. Got it? So next question. Find enthalpy of formation of C2H6 given carbon in the graphite plus O2 gas giving you CO2 gas plus 100 kilocalorie, H2 in the gaseous form plus half of O2 in the gaseous form, you are getting H2O liquid form plus you are having 90 kilocalorie. Then you are having here C2H6 in the gaseous form plus O2 in the gaseous form giving you CO2 in the gaseous form plus H2OL, and here I am writing 200 kilocalorie. Balancing it here 3, you will be getting 7 by 2. Find out the answer and let me know. Any method is fine, Divya and Tejaswini. There is no doubt about it. Fundamentally, you should be right. Let us say this is your reaction number 1, this is your reaction number 2, and this is your reaction number 3. In such kind of question, whatever is asked, you should write down your target reaction first. Your target reaction is this. So you have to find out target reaction means for whom you are finding, for which reaction you are finding basically delta H. So you should write down the reaction first according to this enthalpy of formation. I am not solving it, I am simply writing the target equation. Twice of carbon in the graphite form plus 3H2 in the gaseous form, then you will be writing C2H6 in the gaseous form. For this reaction, you have to find out the enthalpy change, and this is enthalpy of formation of C2H6 gas. No, Kaushik, you check your answer, beta. Some silly mistake you have done. Reshma, absolutely correct. So the thing is, when I am having this reaction, this is your target reaction. This target reaction, what do you want? You want 2 carbon graphite. You will be getting from reaction number 1, but you have to multiply it by 2. You will be writing here 2 into reaction number 1. You want 3H2 on the reactant side. So you are having H2 here on the reactant side by the second reaction. You multiply reaction number 3, reaction number 2 by this coefficient of 3. Then you want C2H6 on the product side, but here it is on the reactant side. Reverse it. Reverse means minus. So simply what I'm going to write down here, and you should also understand one thing, that I have not given you endothermic reaction. For this here, delta H1 will be minus 100. Delta H2 will be minus 90. And here delta H3 is minus 200. So you should not be getting answer as 270. It should be minus 270. Those who are getting plus 270 is wrong. So you'll be having 2 into, this one I can write down. Delta H for the reaction is going to be 2 into delta H1 plus 3 into delta H2 minus delta H3. So minus 200 plus 3 into minus 90 minus of minus 200. So you'll end up with minus 200 minus 270 plus 200. So your ultimate answer is minus 270 kilocalorie. That's your answer. Sai Ganesha, check your calculation term. Vedashri, now correct. Next question. Find enthalpy of formation for N2O5 gas given N2 gas plus O2 gas giving you twice of NO gas. Delta H1 is 10 kilojoule. Twice of NO gas plus O2 gas, it is giving you twice of NO2 gas. Delta H2 is minus 4 kilojoule. Then 4 NO2 gas plus O2 gas giving you twice of N2O5 gas. Delta H3 is minus 3 kilojoule. Find out this answer and let me know. Be careful with the sign which I have given you. I have given you plus 10, minus 4 and minus 3. Raymond, I think you are correct. Likita, check your answer. Mistaken there. Yes, Manas, correct. Now see here, I'm going to write down the target reaction. Your target reaction is enthalpy of formation. That means for N2O5 in the gaseous form, you should be forming 1 mole of it from its constituent element in standard state. So it will be 5/2 O2 gas, right? Now for this reaction, you have to find out delta H, and this reaction is representing the formation of N2O5 gas. Now the thing is, how would you get this target reaction? That's what we have to see. Now let us say this is reaction number 1. This is reaction number 2 and this is your reaction number 3. Now the thing is, you want N2, 1 mole only. It is present in the reaction 1. So I'm saying I just want the reaction 1 as it is. Then you want basically 1 mole of N2O5, but you are having here 2 moles. So basically you multiply here by half, right? So when I multiply by half, same operation has to be done here also. So it will become minus 3/2. Okay, so I want that reaction number 3, but the thing is half has to be multiplied. Then the thing is, when you multiply by half here, you will end up with twice of NO2, and here already when you have taken this, you are having twice of NO. In the desired reaction, that is a target reaction, NO and NO2 are not present. So you are supposed to eliminate them. So you want a reaction in which can cancel out this 2NO. So if 2NO is on the product side, you want a reaction where 2NO is on the reactant side. Similarly, if you want to eliminate 2NO2 here, then in that case you should have 2NO2 on the right hand side. So basically reaction number 2 as it is we'll take up, right? So here I'm going to write down reaction number 2. So that means ultimately I'll be able to write down delta H for the reaction, that is equal to delta H1 plus delta H3 by 2 plus delta H2. So delta H1 is 10, this is minus 3 by 2 and this is minus 4. So we'll be having basically 10 minus 5.5, which is basically 4.5. I hope it is clear. And for those people which is still having a doubt, some of you might be getting, ma'am, how come? So I'm writing that, chalo. Delta H is 10 kilojoule. Now the thing is, what you are adding is half of that, na? Other reaction I'm multiplying by half. So will you be getting there NO gas, NO2 gas plus O2. You are writing twice here, you are multiplying half here, and you are getting basically N2O5, right? And delta H for that, I think we have got by multiplying minus 3 by 2. So the thing is, when I add this up, you will be having N2 plus twice of NO2 plus 3 by 2 O2, and you will be having twice of NO. Everything is in gaseous, I am not writing that. So the delta H for this reaction, this is 1 and 3. Delta H for this reaction comes out to be 10 minus 1.5, which is 8.5. Now this is not the desired reaction because NO2 is extra and here 2NO is extra. So add up your reaction number 2 here. Reaction number 2 is twice of NO plus O2, giving you twice of NO2. Delta H2 here is minus 4. So you add them up. When you add it up, this is gone from here. This is only for explaining those people who didn't get it. Otherwise, you don't have to go for such a long method here. Delta H for the final reaction here, final. This one is for final. You'll be having here 8.5 minus 4, which is giving you 4.5. I hope it is clear. Got it now? I hope there is no confusion. So sometimes if the examiner is giving you some extra reaction there, make sure that you are observing it carefully because majority of the time that extra reaction is for eliminating some extra reactant and product in any reaction. Okay, now let us go for learning the second one, which is enthalpy of combustion. And it is represented by delta HC. Now when it comes to formation, we say formation is always for 1 mole of the product, right? Similarly, combustion means we need to basically combust a reactant, not a product, right? So I'll say that if I take 1 mole of a substance and if I combust it, that means burn it with oxygen. So whatever is the enthalpy change, that is known as enthalpy of combustion. So I'll write down here, it is the enthalpy change. It is the enthalpy change when 1 mole of a substance, is burnt in excess of oxygen gas, right? So for example, if I want to write down C2H6 gas, its enthalpy of combustion, make sure you are taking only 1 mole of it. So in case of enthalpy of formation, we were forming the product. So 1 mole of the product is fixed. In case of combustion, we are combusting a reactant. So 1 mole of that reactant is fixed. So that is the way you remember, okay? So here I'll be writing O2 gas giving you CO2 gas plus H2OL. Here it is 2, here it is 3. So the thing is you'll be getting 7 by 2. Please do not multiply 2 here. It should be only 1 mole. So I should be writing here delta H for this reaction is representing enthalpy of combustion of C2H6 gas. I'll be writing certain compound. Please write down their combustion reaction here. And if at all I'm writing any element, then you should write down its oxide. Write down all these reaction, everyone. And once you are done, let me know. Then we'll proceed further. Arey bhai, there is no response. Are you able to listen? People have written or not? Did you people write it? Finish it? Yes, correct, Raymond. It is absolutely correct, beta. It is correct. So for C6H6, simply you will be writing O2 gas, then CO2 gas plus H2OL. Balance it, this time 6 here, you are writing here 3. You will be writing here 15 by 2. So delta H for this reaction is actually enthalpy of combustion of C6H6 in the liquid form. For aluminium, if at all I am giving you an element, you have to write down its oxide, which is Al2O3 here. So here, this side is fixed that it is 1, 1, 1 only. You cannot change that, right? So here it is like 1/2 you should multiply and oxygen became 3 by 2. So you should write down 3 by 4 here because you want 3 by 2 oxygen atom. Here it is 3 by 2 oxygen atom. Here it will be 3 by 4 into 2. So then only it is 3 by 2 oxygen atom. Got it? So here enthalpy of reaction is actually enthalpy of combustion of aluminium. For graphite, I'll be able to write down O2 gas, giving you what? CO2 gas. Now the thing is here, can I write down this enthalpy of the reaction is representing the enthalpy of combustion of carbon in the graphite form. But it also represents one more thing. Can I say it is also representing the enthalpy of formation of CO2 gas? This piece of information could be important sometime. Are you able to see carbon graphite plus O2 gas? You are writing CO2 gas. So it is telling you that it is the combustion reaction of 1 mole of this particular carbon graphite, right? And it is also forming 1 mole of CO2 now. So I can also say that CO2 is being formed from its constituent element in their standard state. So I can easily write down this is enthalpy of formation of CO2 gas also. Not for every reaction we'll be able to say like that, but wherever it is possible, you should be able to understand. Is there any doubt in this particular reaction here? So I'll be writing here this one, that H2 gas, that to 1 mole of it plus half of O2 gas giving you H2OL, and delta H for this reaction is actually telling you enthalpy of combustion of hydrogen gas, and also it is telling you enthalpy of formation of H2OL. Are you able to understand this part, everyone? Yes, very good. Those who got all correct, wonderful. Can we proceed further now? Good. So the thing is, why I am giving you a practice of writing enthalpy of combustion or enthalpy of formation is, unless and until you know how to write down the reaction, then you cannot proceed further. Getting it? Now, let us go for the next thing here. So I am writing delta H for the reaction. The same way we have written the formula if at all enthalpy of formation is given. Similarly, enthalpy of combustion could also be given here. So in that case, what you have to do? Summation of enthalpy of combustion of the reactant minus summation of enthalpy of combustion for the product. This is for reactant. In fact, you have already written, so why to write it? So when enthalpy of combustion data for reactant and product is given. Now the thing is, always remember, when we go for formation, we are forming a product, right? So always you are doing enthalpy of formation of the product minus the enthalpy of formation of reactant. But when we are going for combustion, we are doing the combustion of a reactant. So we are writing enthalpy of combustion data of the reactant minus enthalpy of combustion data for the product. Is this point clear? Right? And one more thing is this combustion always an exothermic process? If it is an exothermic process, then the enthalpy of combustion will be negative here, always negative. There is no doubt about it. So I'll write down here, delta Hc is always negative. That is, delta Hc is always less than 0. There is no doubt about it. I'm going to give you a question. Please find out that. Find delta H for the reaction. I'm giving you reaction here. C2H2 gaseous plus H2 gaseous. You are getting C2H6 gaseous. Given enthalpy of combustion for C2H2 is minus 100 kilocalorie. Enthalpy of combustion of hydrogen is minus 20 kilocalorie. Enthalpy of combustion of C2H6 is minus 200 kilocalorie. Everything is per mole per mole. Find it out. Reshma, did you balance the reaction? Those who are repeating, those who are writing 80, they didn't check out that I didn't give you a balanced reaction. Those who are reporting plus 80, they didn't balance the reaction. Every time examiner may not give you balanced reaction. Correct. Plus 60 is correct answer. You have to balance it, okay? I didn't balance it. So the thing is, delta H for the reaction, that is going to be summation of enthalpy of combustion of the reactant minus enthalpy of combustion of the product. So here I'll be writing for the reactant, that means minus 100 plus 2 into minus 20 minus of minus 200. So I'll be writing minus 140 plus 200, which is basically 60 plus 60 kilocalorie per mole. So do not be in hurry. Check it out whether the examiner has given you a balanced reaction or not. Then next question, find enthalpy of formation of C2H6 gas given enthalpy of combustion of carbon in the graphite form, that is minus x1 kilojoule per mole. Similarly, enthalpy of combustion for the hydrogen gas is minus x2 kilojoule per mole. and enthalpy of combustion of C2H6 in the gaseous form is minus x3 kilojoule per mole. Now my question to you people is, how would you, like, whether you will go for reactant minus product here or product minus reactant here? Tell me. You have to find out the enthalpy of formation for C2H6, whether you are going to write down reactant minus product or product minus reactant here. Reshma is writing product minus reactant. What about rest of the people? Gautami also the same thing. Reactant minus product. I think Amrut, Anand, product minus reactant. Pravalika also. Pravalika, okay. Now the thing is, you people are mistaken there. Those who are writing reactant minus product are absolutely correct. The thing is, you first of all write down the equation according to what is asked in the question. You always write down the reaction according to what is asked in the question. What is asked in the question? Formation reaction. So you write down the formation reaction here. So formation reaction will be 1 mole of this C2H6 gas. You'll be forming it from 2 carbon graphite plus you'll be writing 3H2 gas, right? You're going to form 1 mole of this, right? Now the thing is, for this reaction only you have to find out delta H, and this reaction is representing the enthalpy of formation of C2H6 gas. Able to understand first of all? You write down the reaction according to what is asked in the question. Asked in the question is enthalpy of formation. So you've written, right? And basically enthalpy of formation is also a reaction now, right? Now how do you find out delta H of a reaction? If at all enthalpy of combustion data is given, then you come to see what is the data, what is the format in which data is given, whether the enthalpy of combustion or whether it is the enthalpy of formation which is given. So if combustion data is given, always go for reactant minus product. Okay. So here I'll be able to write down delta H for the reaction, that is equal to summation of enthalpy of combustion of the reactant minus enthalpy of combustion of product. Always go like that, you'll never go wrong here. So reactant is this one, so minus 2x1 minus 3x2 plus x3, that should be your answer. Minus 2x1 minus 3x2 plus x3. Understood everybody? So simply what is asked in the question, according to that you write down the reaction. After that, just treat it like a normal reaction, right? And then you see what data is given to you. Is it the enthalpy of formation or else it is the enthalpy of combustion? If formation data is given, simply apply product minus reactant. If combustion data is given, reactant minus product. So if you keep this thing clear in your mind, you'll never get confused. Okay? Got this everyone? Then I'll give you one last question. After that we are going to disperse here. There should not be any confusion. Okay? Chalo. Next question. Last question in fact. Find enthalpy of combustion of C2H4 given standard enthalpy or else enthalpy of formation of C2H4 gaseous is minus x1 kilojoule per mole. Enthalpy of formation of CO2 gas is plus x2 kilojoule per mole. Enthalpy of formation of H2O liquid can be minus x3 kilojoule per mole. All of you please find it out. And do remember, enthalpy of formation could be positive or negative, right? It could be positive or negative. And you need not worry and make sure that what is the way I have gone, given you the data. So this time you are going to write down the equation like this. Will you do product minus reactant or reactant minus product? Tell me. Will you do product minus reactant or reactant minus product? This time, reactant minus x1. You should be able to get this. All of you got this? Right? So fine, we'll wind up here itself, right? Hopefully everyone got this, right? So I'm just sharing it, the QR code. Revise the things and solve the question. Read the language of the problem correctly. Yes, correct. Check your answer, beta. Ganeshwar Sai, please check here. Everything I have solved it. What is that GG there, beta? है ना? You can simply say, got it, ma'am. है ना? Write this down and please scan it. Okay. Please revise the things and all of you can now disperse for your lunch. Okay. Thank you and have a nice day. I hope it is scanned now, beta. Everybody. Shanvi, it's not necessary, beta. You are having the old NCRT now. That's okay. Only thing is, it shouldn't be very old. I mean,